Part 2, reactivity of N-heterocyclic carbenes with different HF sources. Now, imidazolium fluoride falls into the category of naked fluoride reagents. Here is the family of known naked fluoride reagents with its beneficial or wanted properties. Now, I don't have time to go into details about their properties. However, it suffices to say, to the best of my knowledge, I haven't been able to find a single example of a naked fluoride reagent that would be chemically stable, at least in acetonitrile. And significant advances are to be made in their anhydrous synthesis. And I'll tell you why. The general synthesis procedure of all of these is that you take a different halide salt, namely chloride, bromide, and iodine, and then perform a metathetic or substitution reaction with different metal fluorides, mostly alkali metal fluorides. And this brings us to the problem which I'm talking about throughout this lecture. Alkali metal fluorides are scarcely soluble in solvents. That's why you have to perform this reaction in the presence of water. But you don't want to do that. And you don't want to do that because reactivity of fluoride anion is highly dependent on its environment. And water usually deactivates and changes its reactivity, and you don't want it to be present in the reaction mixture. Moreover, by doing substitution reaction, you get, of course, your product, but with it another MX salt. And the research on this field showed that purification and isolation of anhydrous imidazolium fluoride product is difficult. And what we envisioned is, well, we have imidazolium chloride, but then we said we're not going with the metathetical mechanism. Why don't we go by established synthesis procedure to N-heterocyclic Carbene and then try to perform addition of hydrogen fluoride to the Carbene? And I took Carbene and mixed it with anhydrous hydrogen fluoride, which acted as a solvent and as a reagent. And I just hoped it doesn't destroy my substrate, it doesn't react differently, or it doesn't burn it. Luckily, it didn't, but it didn't give me imidazolium fluoride either. What it gave me is imidazolium polyhydrogen fluoride. And we managed to fully characterize this product, and here I would like to note this is not a fluoride reagent because these two HF molecules can get dissociated, so this is an acidic reagent or HF reagent. But we were kind of on the right way because if with surplus or 3 equivalents the reaction yields polyhydrogen fluoride, then the question arose, can we then by stoichiometric quantities with 2 equivalents get bifluoride anion and finally with 1 our wanted reagent? And then we had to solve the problem of anhydrous hydrogen fluoride, and we successfully find its replacement, which is 3-ethylamine 3-hydrogen fluoride complex, which is just a milder version. And when I repeated the reaction with surplus of this one, the reaction gave me the same result, and that made me rather happy. And luckily then with 2 equivalents I got my bifluoride product, and finally with 1 my wanted imidazolium fluoride reagent. Here are the crystal structures that are also interesting for several reasons, and I don't have time to go into it. And here we can see our fluoride anion loosely stabilized by 4 hydrogen bonds in a crystal structure. But the interesting thing starts to happen not in crystal structure but in solution. That's why I would like to show you superimposed spectra of all 3 anions. On the far right we get dihydrogen 3 fluoride. On the opposite scale we get a characteristic doublet signal for bifluoride anion, and almost at the same chemical shift we get a singlet peak for imidazolium fluoride. Now, why am I showing you this? I'm showing you this because I've grown monocrystals of imidazolium fluoride. I took it to X-ray analysis, got parameters for the crystal cell and everything, and then dissolved the crystals in deuterated acetonitrile. And when I took this sample on NMR analysis, it showed me this peak. And this is confusing and strange because this peak corresponds to bifluoride anion. And this set us back for about 3 weeks or almost a month. And a valuable lesson was learned that sometimes you have to be patient with chemistry and you just have to wait a little bit. Because if you leave this sample standing for another day or so, the doublet peak is gone, and again a singlet peak characteristic for imidazolium fluoride can be observed. But do you know what this means? This means that two imidazolium fluorides in acetonitrile, they react and form bifluoride and free carbene moiety as a kinetically controlled products. And with time, reaction goes back and thermodynamically more stable imidazolium fluoride forms. Which, if you think, is rather interesting. Two imidazolium salts form free carbene molecule. This type of chemistry hasn't been observed before. If we now take a look at the whole reaction scheme overview, we said, well, if one transforms into two and back, we said, of course, if we prepare pure bifluoride compound and react it with additional equivalent of carbene, would that go to monofluoride product? And of course, the answer was yes. But then we thought, well, we know one bifluoride molecule that is not dangerous, it's not harmful, it's stable on air, it's widely used in industrial level and really cheap, and that is potassium bifluoride. And we thought, what if we react carbene with potassium bifluoride? And the reaction got us the same result. So now we had a really elegant and easy way how to prepare analytically pure anhydrous imidazolium fluoride on a gram scale. And if I just briefly return to the beneficial properties, we see that we managed to derive a simple anhydrous synthesis of our product, and most importantly, we show that it's thermodynamically stable in acetonitrile. And these last two check boxes are actually the added value here in the field of naked fluoride reagents. So if we go run through, so we derived anhydrous synthesis of a novel naked fluoride reagent. We additionally synthesized two other polyhydrogen fluoride salts. All three were synthesized using different sources of HF, which demonstrates the versatility of the applied synthetic approach. And all three were isolated in high yields and high purity.